Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Complex Numbers Part 2, Algebra, and we want to look at the factor theorem and quadratic formula. Now in the previous video in Part 1, we also covered algebra, but we covered rationalizing the denominator and finding square roots of complex numbers. So in this one, we're going to focus on factor theorem and quadratic formula. So let's get right to it and let's look at our first question here. Says verify that u is a root of the equation z cubed minus 8z plus 8 root 3 equals 0 and state the other complex root of this equation. Now let's go back to the board here. And I've already written what u is. U was given in the previous part of the question. U is root 3 plus 1, and it gives us this equation z cubed minus 8z plus 8 root 3 equals 0. And it asks us to verify that u is a root of this polynomial. So this follows factor theorem. If you have a factor of the polynomial, then your factor will be a root of the polynomial. And you can verify this two different ways. For this question, I'm going to show you one way. And then in the next question, I'll show you a different way. Okay, so we'll use what we learned in further algebra with polynomials. How that when you have the factor theorem, and if u is a factor or a root of this polynomial, then z of u, that is evaluating this function, plugging in the u, should equal 0. So we're going to plug u in. U is root 3 plus I. We plug it in for z. We're just evaluating the function. Root 3 plus I cubed minus 8 times root 3 plus I plus 8 root 3 equals 0. We want to demonstrate that this is true. Well, here we have a cube. And so unless you're really good with Pascal's triangle and working this out as a binomial expansion, you might want to just manually do it yourself. So here is your root 3 plus I times root 3 plus I. And you can, of course, do the smiley face method. This one times this one, this times this, this times this, this times this. And so your root 3 times root 3 is 3. And your I root 3 and I root 3 make 2I root 3 plus I squared. I squared is a negative 1. 3 minus 1 is 2 plus 2 root 3i. So multiplying those two together give us 2 factors of u. We want 3 factors of u. So we'll multiply it by 1 more and do the smiley face method. 2 times root 3 is 2 root 3. 2 root 3i times I is 2 root 3i squared. And 2 times I is 2i. 2 root 3i times root 3. The root 3's make 3 times 2 is 6, gives us 6i. Our I squared simplifies to a negative 1. So we get 2 root 3 minus 2 root 3 plus 8i. So these two cancel out and just leave us with 8i as the cube of root 3 plus I. Then we distribute the negative 8 through, and we get negative 8 root 3 minus 8i, and here we have 8 root 3. So you can see that the negative 8 root 3 cancels with the 8 root 3, the 8i minus 8i also cancels, and we're left with 0 equals 0. Now remember, for this particular question, we're not solving anything. We're simply verifying that u is a root of the polynomial. So since we were able to plug it in and get 0 equals 0, Therefore, u equals root 3 plus I is a root. And it also asked us to state the other complex root of this polynomial. So if root 3 plus I is one root, then the conjugate is root 3 minus I. So here are our two, our conjugate pairs of complex numbers. And then, of course, there would be one real root, but it doesn't ask us to find that. So that's our first question. Let me set up for the second one here. Okay, let's look at our second problem here. It's similar to the first one. It says it is given that the complex number -1 plus root 3i is a root of the equation where, and here's this polynomial, and where k is a real constant. So it wants us to write down another root of the equation. And then for the second part, it wants us to find the value of k, and it wants us to find the third root in the equation. Notice this one is 6 points. So it's a little similar in the question as the previous one, where we had a root and we had a polynomial. But instead of simply saying verify that it's a root and find the other root, it wants us to find the other root, and then it wants us to solve for k, and it wants us to give the third root, because there's 3 roots to this. So, and the third root. Okay, so let's do the easy part first. Let's do the other root. If one root is a -1 plus root 3i, then the other root is -1 minus root 3i. So that's that part there. That's quite easy. Now, in this particular example, they didn't give us the variable in front, like u equals or z equals. So we can see from the polynomial that this is going to be x. X equals the -1 plus root 3i. X equals -1 minus root 3i. Now we need to solve for k, and we need to find that third root. So what we're going to do is we're going to take the 2 roots that we have, and we're going to move it into the factor form. So remember, the root is the solution form, x equals, and now we want to go from the solution form and change it into what it would look like as a factor. So if we add 1 to the other side, we get x plus 1, subtract the root 3i. So instead of it being the solution, it is now one of the factors of this polynomial. And if we take the other one and do the same thing, we add 1 over, so we get x plus 1 plus root 3i. So now we have 2 out of the 3 factors that are involved in this polynomial. And we're going to multiply these 2 together. And so you get root 3i times negative root 3i is a negative 3i squared. So I put it over here in the constant column. Root 3i times 1 is root 3i. Root 3i times x is it's a positive root 3ix. Then we go to the 1. 1 times the negative root 3i is negative root 3i. Make sure you keep your columns in order. 1 times 1 is 1. That goes in the constant column. Notice, remember, I squared changes to a -1. So this is going to be a constant. 1 times x is x, and so I put it all the way over here because there isn't an x column yet. So we have our constant column, our root 3i column, our root 3ix column, and then just the x. Then we multiply x. X times negative root 3i is negative root 3ix. So put it in that column. 1 times x is x, and x times x is x squared. We add this all together. Remember that your I squared is a -1. So that gives us a positive 3 plus 1 is 4. I suppose I could have put that, maybe I'll put that over here at the end. And here, this root 3i and negative root 3i cancel. Root 3ix and negative root 3ix also cancels. X plus x is 2x, and of course the x squared. So we end up with x squared plus 2x plus 4 is the combination of our two roots changed into factors and then multiplied together. So if we want to find the third root and also solve for k in the process, we can divide this quadratic into our cubic, and when we divide this into the cubic, our remainder is the third root. So instead of doing it with the function notation like we did in the previous example, where I just did the function evaluated for the root, in this case, we're going to do long division. And actually, I'm going to use synthetic division because it's a little faster than long division. So with synthetic division, you just write your coefficients down. Here's the cube, here's the square, here's the x, here's the constant. And we take our divisor and we change the sign. So instead of plus 4, it's minus 4. That's this first row. And then in the next row, we bring down and change the sign again. The coefficient's negative 2. And in the front, there is a understood 1. So we don't have to worry about that when we're dividing with synthetic division. Only if there's a number other than 1, then we need to put a divide by that down here. Since it's a 1, we're okay. So we bring down our first number, k, and multiply. So we get negative 4k. That should be 1, 2, 3 values in. 1, 2, 3 values in. That's over here, negative 4k. K times negative 2 is negative 2k. It goes right here. So this right here adds up to 5 minus 2k. Then we multiply this. That gives us a negative 20 plus 8k. And this one times this gives us a negative 10 plus 4k. And if we notice, if we take a cube divided by a square, x cubed divided by x squared is x. So this is the x column. This is the constant column. And everything after the constant column is then the remainder. And since these are both roots, this is a combination of roots, our remainder needs to come out to 0. And if you notice here, 10 minus 10 cancels out. Negative 4k plus 4k, this does cancel out to be 0. Here we have this, and this creates for us a nice little equation where we can solve k. So we're going to have 8k minus 16 equals 0. 8k equals 16. Therefore, k equals 2. So that's one of our answers there. It said find k. K equals 2. So if we plug k into here, this is 2. 5 minus 4 is 1. It asked for the third root. The third root is is 2x plus 1 equals 0. Okay, this is the factor that's left. Then to solve for it, to get the root, we have 2x equals negative 1 and x equals negative 1/2 is the root. The root is the solution. That's different from asking for a factor or a prime factorization. Okay, so be careful that you keep in mind your equation, your factors, which would be this is 1, this one's the second one, and this one is the third one, and also your roots, which are the 3 solutions. Okay, so in this one, instead of using the function, evaluating a function for the factor theorem, in this one, chose to do, because we needed to find the third root and we needed to solve for a variable. For this one, I chose to use synthetic division to help us with that one. So depending on how the question is asked, you could use either one, the function evaluation or the synthetic division. Okay, so let's try a different one. Okay, let's look at our next example here. A little different question type. Says the complex numbers u and w are such that u minus w equals 2i and u times w equals 6. Find u and w, giving your answers in the form of x plus iy, where x and y are real and exact, and it's 5 points. So let's go back to the board here. Here we're given find u and w. These are like vector forms in the x plus yi format. And the relationship between the two, they give us two equations. It's like simultaneous equations, but now we're doing it with imaginary numbers. So u minus w equals 2i and u times w equals 6. So like I mentioned in the previous video, all of your algebra skills that you learned before, you can still use now. You're just incorporating the imaginary number component in your skill set. So that's what we're practicing here, some simultaneous equations. So we're going to get u by itself. And so we divide by w and get 6 over w. And then we're going to substitute that into our first equation. And we get 6 over w minus w equals 2i. And just like we normally do in algebra, we want to get rid of the fraction out of our equation. So we're going to multiply everything through both sides by w. That gives us 6 minus w squared equals 2iw. We notice that we have a quadratic here, so we're going to set everything on one side equal to 0 in decreasing exponential order. So we'll add the w squared to the other side. We'll keep the 2iw here, and we'll subtract the 6 over. And so that gives us w squared plus 2iw minus 6 equals 0. Notice it's the w that is our variable that we're solving for. Factoring is now going to be a little bit more challenging than it was previously because we have a mixture of real and imaginary components. So I wouldn't suggest that you try factoring unless it's quite obvious that it works. So what we're going to do is we're going to use the quadratic formula, and the quadratic formula works exactly the same way as it did before. So we're going to get w, because we're solving for our variable, which is the w here. So w equals a negative b, so minus 2i, it's okay, don't worry about the imaginary number, plus or minus root b squared, so that's a 2i squared, minus 4, a is a 1, and c is a negative 6, all over 2 times a being 1. So the first thing that I do is I like to reduce my radical here. So this simplifies to 4i squared, and this is plus 24. Remember that I squared is a negative 1, so this is a negative 4 plus 24, which is root 20, and root 20 is 4 times 5, and root 4 it comes out as a 2. So this is 2 root 5 is simplifying that radical of root 20. Okay? So if you put root 20 in your calculator, it might simplify it for you down to 2 root 5. And so what we have now is w equals a negative 2i plus or minus 2 root 5 over 2. Now, before we continue with this, let me just point out something here. This particular one turned out rather nice. However, it is possible to get a rather difficult one where you have an imaginary number in the radical. Our imaginary number, our I squared, canceled out as a negative 1, And so we just ended up with numbers in there. It is possible to end up with, let's say instead of 4i squared plus 24, maybe you have 4 plus 24i. Okay? And it's in a square root. So if that happens, okay, so like just for example, if instead of it being like this, it was 4 plus 24i, where the imaginary part didn't cancel out, then at this point, you would go back to what we learned in the previous video about square roots. You would set this equal to a plus bi. You would then square both sides to get rid of this, and you would solve for the two roots of this. You have to solve for that a and b part. So just like what we did in the previous video, you can go back to that to review if you need to, and you will get your two roots, and they'll be in imaginary numbers, and then you can plug them back into this spot right here. So ours reduced out nicely. We didn't have to do that, but it doesn't always come out nice. It can still be a little bit difficult. And so you'll have to take that, work it out like we did with square roots, and then take that result and then plug it back into this part of the formula. So that would be kind of an extreme case. And I have seen those questions show up in previous past papers, but it's been a while, and I'm not sure yet how the 2020 syllabus cycle is going to play out, whether they will go back to those kind of difficult questions or not. But so far, what we see here, it turned out nicely for us. Now we can distribute this 2 through our division, because division distributes through our add and subtract. And so we get W equals now a negative I plus or minus root 5. And we can switch that around so that our plus or minus root 5 is in the front, because that's the real component, minus I. Now keep track of your plus and minus, keep the order so that you can follow it through the rest of the problem. Now we're going to take this and we're going to move it up here into, now that we have W, we want to find our U. So U equals 6 over plus or minus root 5 minus I. Well, now we have an radical in the denominator. So again, we're going to use the same skill that we demonstrated in the previous video on how to rationalize the denominator. We're going to multiply top and bottom by plus or minus root 5 minus I, or sorry, plus I, because this one is minus, so we switch this one to plus, top and bottom. And when we distribute that, we get U equals, here we have a plus or minus 6 root 5 plus 6I all over root 5 times root 5. It doesn't really matter whether it's positive times positive or negative times negative, comes out as 5. And then the minus I squared. Remember, I squared is a negative 1. So that becomes plus 1, and we end up with 6 on the bottom. So we have a total here of 6. The 6's also cancel out, so we end up with U equaling plus or minus root 5 and plus I. Okay. So when we write it out here, we get when U is the plus root 5 plus I. When it's the positive, the W is also the positive root 5 minus the I. And when U is the negative root 5 plus the I, the W is the negative root 5 minus the I. Okay, so that goes together there. And these then are the solutions for U and W, two sets of solutions that satisfy these two equations. Again, the reason why we got two sets is because we ended up with a quadratic in there. And here is our UW combinations that make this a true statement. So this one is using some different skill sets, but all algebraic sets or skills that you learned previously, and you're just now applying it to the imaginary numbers. So you have the quadratic formula, you have rationalizing the denominator. Just keep track of your plus and minus so that you know which one goes with which. But everything stayed in the same order. So the positives went together and the negatives went together. Okay, I got one more for you, and let's see what it looks like. Okay, let's look at our last problem for this video here. And we have find the complex number z that satisfies the equation z plus iz over z star, or you could call it z asterisk, minus 2 equals 0, where z asterisk or z star denotes the complex conjugate of z. Give your answer in the x plus iy form where x and y are real. It's worth 5 points. So that means we have about 7 minutes to do this problem. And we are solving this equation. We want to find z. Well, we're told that z and z prime are conjugates. So we're going to use that to help us solve this. The order in which you do this is kind of up to you. You can substitute in first, or you can clear the fractions. Let's just go ahead and clear the fractions. So we're going to multiply everything by z asterisk or z star so that we can cancel out what we have here. So we end up with z times z star. Here they cancel, so that just leaves us with iz minus 2 equals 0. Now at this point, we're going to substitute in the format for the z and z star. So z would be x plus yi, and the conjugate is going to be x minus yi. Plus I times z, z is the x plus yi minus 2, and all of this equals 0. So we can go ahead and multiply this out. So when we multiply this out, we get x squared, a plus xy and minus xy. Remember, conjugate pairs give you a difference of squares, so that means the nose and the mouth cancel out. When we multiply the last term, we get minus y squared I squared. Then we get plus ix and plus yi squared minus 2 equals 0. So just carefully multiply all those out. Our I squareds become negative 1. And so when we put this together, we end up with x squared plus y squared. Here, minus 2. All of this is, none of these have an I in it. So this is all the real component. And then we have, here we have plus ix equals 0. And I feel like I'm missing something here. 2y, where's the 2y? Let me just look at this really quick. Okay, sorry about that. I found my mistake when I multiplied the z star through. I forgot to put it on the 2, so I went back and fixed it. I distributed it to everything else, but I forgot to put it on the 2. So when we plug in, this should be a minus 2 times the conjugate, x minus yi. So when we multiply this out, we got our x squared minus y squared I squared plus ix plus yi squared. Then distribute this, minus 2x plus 2yi equals 0. Substitute the negative ones for our I squared. So we get our x squared plus y squared minus 2x and minus y. All of these are the real, none of these have an imaginary in it. And then we have our ix plus 2yi that have the imaginary components. So since this equals 0, then technically it's like 0 plus 0i. All of this is supposed to cancel out, meaning all of the reals are supposed to cancel out and all of the imaginaries are supposed to cancel out. So we're going to use that and create two separate equations. X squared plus y squared minus 2x minus y equals 0. That's the real component. And we also have x plus 2y equals 0. That's the imaginary component. So from this, we now have x equals negative 2y. We can plug that back up into this one. So we get negative 2y squared plus y squared minus 2 times negative 2y minus y equals 0. So this here gives us 4y squared plus y squared plus 4y minus y equals 0. That gives us 5y squared plus 3y equals 0. Factor it, we get y times 5y plus 3 equals 0. So that would give us y equals 0. Well, we don't want a y equals 0. That means everything's 0. We want actual value. So from this one, we get y equals a negative 3/5. Y equals negative 3/5. Plug that back in up here. So we'll put that up here. So x equals negative 2 times negative 3/5. So x equals a positive 6/5. So for our z equals 6/5, that's the x value, minus 3/5 I. Here is our z factor, 6/5 minus 3/5 I. The conjugate of z would be 6/5 plus 3/5 I. It doesn't ask for the conjugate, but if you were to plug those in, you would see that it would indeed come up to 0. So here again, we cleared our fractions by multiplying through the conjugate. Make sure you distribute all the way through. And plug in your x plus yi and x minus yi. We can't solve this the way it is right now. So by plugging in our x plus yi, x minus yi, we generate this equation here where we have reals and imaginaries, and then we equate coefficients, realizing that all of this is supposed to cancel out. So we set the real part equal to 0, the imaginary part equal to 0. Solve for one of your variables, plug it back in, it's just simultaneous equations until you get your two answers. Then you can put together your final vector form, z equals 6/5 minus 3/5 I. So hopefully you recognize most of the skill types that we've used in algebra before, and now just applying it to the complex numbers. Of course, you have to be careful, you have to understand the notation, but the skills are actually basically the same as before. So thanks again for joining me in the Zoom room. Hope to see you next time for part 3, where we look at the trigonometric and exponential platform for complex numbers.